Hey, what's up? So in a previous video, we talked about how we can model system calls or audit system calls to try to understand whether or not they're susceptible to command injection vulnerabilities. There's a number of ways this can happen. We can use different sinks instead of system. We can use different sources. But one of the ways that we decided to model this was based off of Pwn to Own Tokyo. This was Team Flashback or Flashback Teams, Pedro and Radek, did a really awesome video on YouTube, and I'll post it in the description. Essentially, they have a TP-Link Archer A7. It's MIPS architecture. The firmware version is 190726, so I went and got this firmware version. And just with 7-zip, you can extract the file system and pull out this TDP server that has a vulnerable system call in it. So we wanted to take a look at sort of like what the process is for modeling this stuff with Ghidra P code. And now in this video, I'm going to contrast that a little bit by talking about how we can do this in Binary Ninja's high-level IL. There aren't too many differences between this high-level IL and the medium-level IL for doing this, so I'm just going to do it in high-level IL. Things do change quite a bit when you go into the low-level IL. So if you saw my video on doing this in Ghidra, essentially it seemed like it was like kind of pulling teeth to get information about certain variables and how they correlate back to stack and stuff like that. That's not really the case with Binary Ninja, but there are some weird quirks, and I want to cover those things too, right? So essentially we're going to be doing the same thing. If I go to Ghidra, if you haven't seen the video, essentially this is what we're building. All right, so we run this. There's 464 functions in this. It finds three good targets to analyze. And out of those, it starts taking a look. This one is a false positive, which is wrong. And then this one is a true positive, which ends up being the actual location where there is a command injection vulnerability. Verifying this and doing all the reverse engineering to get data here was very complicated from looking at Flashback Team's work that they did. But bottom line is it gives us a good point of interest of where to look and focus our efforts. So that's what we're essentially trying to build. We're trying to model this one case, okay? So in this particular case, if we go here, this system command is formatted with snprintf. There's a Lua command that gets executed down here, and turns out you can inject into this mac %s here to this variable. So we're actually done with Ghidra. We don't need that anymore. So we'll open up Binary Ninja. The way that I'm going to be loading and doing analysis here has been using the command palette and the snippets editor. If you have, if you have Binary Ninja, to use the headless mode that I'll be using for testing, you need to have the commercial version. If you're a student, you can basically go into the command palette, go to the managers plugin, and then just type in snippets on the snippet UI. You can just download or install over here. I already have it installed. And then from here, you can launch and manage snippets and stuff. So I have my snippets directory where things are stored. Actually, not right there at all. I will have it open where things are stored in code. Okay, so I have a TDP server, which is just the binary. I have my own binary ninja database that I've already saved with a variable named. And then we can kind of show how this works. So I'm going to run this. And this is essentially the same thing that the Ghidra script did, but instead it's using Binary Ninja. So one thing to notice here is I really try to model everything doing the same technique, same sources, same sync. But what we have here is only one alert instead of two. And it may look like there was some magic under the hood that prevented the false positive from occurring, but it really should have. And I'll kind of talk about why it didn't happen, and sort of the things that we have to do in Binary Ninja, which is a little bit different. So Binary Ninja is a little bit like pedantic in like how you need to format things. If this is going to be really bad, I think I'm gonna get crap for this, but if Ghidra is JavaScript, then Binary Ninja is TypeScript. Things are like very well structured. It's in Ghidra, I feel like I have an object to something and I'm going to traverse this object until I get the thing that I need, and then I'll work my way back down into something, a reference for something that I need to work with. In Binary Ninja, like things are just like so much nicer. It seems like they actually decided to give everyone the information from the various levels of IL before building out the API instead of it being an afterthought where you're doing a lot of extra stuff yourself that you feel like should just be a part of the API in general. So we'll kind of discover that stuff as we look into this. I wanted to basically go down the the path of analyzing like what this actually is rather than typing it all up. All of this code will be on GitHub gist that I'll post in the description. So here we go. All right, so this is just a normal Python script with a main function. We want that so we can bail out early if there's nothing that looks like it's analyzable. So we have binary ninja imported here. Again, this is for our headless. I have some sources, so we're going to be taking sort of a shortcut in the way that we take a look at sources, right? So sources can be data from a file, it can be from a socket receive, it could be from USB, it could be from like anything, right? But in this case, in the case of this particular vulnerability that we're looking for with OS command injection, this is a common pattern that you'll see. You'll have some definite structure to a command that you want to run, but some unknown data based on like a configuration setting or something that the user does. And then that gets smashed together and passed to system. So we can sort of cheat and make our analysis a lot easier by just shortcutting all of that and saying it's probably going to be passed to some format function. I'm going to be using snprintf and sprintf, but you can use whatever other format string functions are available. There's lots, right? System could be system. Sometimes it shows up as like underscore system, so you have to look for those types of things. Popen, it could be execve. There's lots of different ways that it could be, but the most general way that you see on these types of devices is just system, right? So that's what we'll look for. We know that TDP server is vulnerable. What we could do is basically just churn through lots and lots of basically an entire file system on an IoT device and just analyze every single one of them really, really fast and have sort of like a report. This binary, go to this function at this address and take a look at this, right? And that's what we're trying to accomplish here. So there's 3 steps that we're going to be looking for. The first step is we're going to check and see if the source, the target binary has system and at least one source. So snprintf or sprintf. If it doesn't, then we're just going to leave. There's no reason to do any more. If that is the case, then we need to find functions. We're making another assumption here. We're going to find functions that call both system and snprintf or sprintf. We're going to assume that both of those things happen in the same function. If you don't make that assumption, then you have to basically trace how inputs come into that function, where it's called from, resolve all of those. Any return values from other functions that are being called inside of your target function where system is need to be analyzed, the outputs analyzed. So there's a lot more work that needs to be done, 100% possible, but it's a lot more code, right? So we're gonna be cheap here and look for the low-hanging fruit. And this is, I think, a very good assumption to make to simplify analysis. And I think it makes sense in a lot of different cases. So I don't think we're losing too much. Okay. So in step 2, when we find all these functions that have a source, a call to a source and a sink, then we're ready to move on from there. We'll just print out some details, and then we'll dig deep into these, what we'll call interesting functions. From here, we can use high-level IL, look for calls. There's one case where there's a call assignment wrapped up into an assign, and we'll see how that looks. So we have to handle that. And then we'll basically just look at each one of those. So we're going to get the first parameter to our source and the first parameter to our sink. And then if those two things are the same, then we just alert. It's a really simple thing. Certain things could happen, right? So like from our format string specifier, there could be a sanitization function that looks at the concatenated thing that you're trying to execute and may do verification that doesn't have any like dot dot slashes or something else in it, right? Usually that would happen prior to the formatting of the string. So I don't think this has really happened too much, but it's very possible. So again, there could be false positives because we're at the sake of getting false positives, we're trying to make our analysis faster, easier, simpler to write, that kind of stuff, right? So we can continue to layer on more complexity here. And this is really what I feel is kind of like the bare minimum that we need to get a decent type of analysis and points of interest out of this, okay? All right, so again, these are the sort of like the 3 blocks. We can ignore this stuff here. But essentially it says this target contains an interesting source and sink, which it does. There's 3 functions to analyze. So out of those 464, Binary Ninja and this script have decided that there are only 3 targets that are worth any more analysis at all. And in that analysis, we found that this one has a call to snprintf, and the call to system doesn't appear. So why doesn't the call to system appear? And this is the same thing that happened in Hydra. So let's go to this location. So there's our SNPrintf. System actually appears. It's actually rolled up in high-level IL, so it doesn't appear on its own. So what we're doing is we're stepping through. Let's see if I can make this a little easier to see. So here's our call. So if we're looking through the IL and we get to this location, this operation, what's really nice about this is I have the ability to do things like current HLIL, which will give me this current function. And then I can index into that. So this instruction right here is at index 288, and then I could just get that. Super cool. So then I could just do operation, and and that's a HILL call, right? So the fact that this one is a call, what I'd really have to do is do something like prefix operands or postfix operands, and look at everything in here. And then what I can see is as I'm pulling this apart and walking this, I can kind of treat this like a stack and start popping things off to handle everything. At this location, I can see that, that's a call. Where's that target? Oh, that system. Now I can verify that. Turns out that it doesn't matter because what ends up happening is this system is just calling a static string that exists in the binary. So we're not really missing out here, but we essentially missed a potential target to analyze and we skipped over it because we didn't see where system was called. Because the way that we actually do the checking for where system is called is sort of naive, right? So all of this stuff is fine and simple. Let me just kind of go through this real quick and then we'll address this. I feel like I'm skipping around, so apologize for that. So we'll load up TDP server. Binary Ninja will analyze it, and we're going to say, get us all the symbols. So rather than looking through potentially thousands of functions and saying, hey, do you call a source in a sink? Hey, do you call a source in a sink? What I'm going to do is ask the binary and say, do you have system and one of my sources and one of my sinks? You do. That's wonderful. So the way that we do that is we could say either get symbols to get all of the symbols for the binary or just get specific types. Now there's lots of types, and if you're doing like PE files, there'll be function symbols instead of like imported symbols, so just be careful there. But in this particular case, I can narrow it down and say I just want all of the symbols. So like give me all of your imports. And from those, I'm just basically saying give me the name for that object. And if that exists inside of sources, I'm going to go ahead and slap that onto source symbols. Then I'll go ahead and take a look at the set to find the intersection between those two sets. And then if there is one, like meaning there's something that results out of that, we know that we have a source, we know that we have a sink, and we can continue analysis. There's really nothing that special to that. This is the most special thing here. After this point, what we can do is get function at. So what we have is we have these source symbols. Up here, we appended them as the actual object, not the name, so we can still work with them. So at this point, I need to go figure out where those things are actually being called from. So I know that I have these references that are called from different points in the binary. The way that I'm going to do that is to say get function at. This function reference is going to be my source. So if it was snprintf or sprintf, this is the location where that function actually exists, and it may jump to an external. It may end up being like statically linked or something like that, but this is the function, right? And then I just basically am going to say, give me all the callers. That's it. That's all you have to do. There's no special thing with getting function managers or doing any of this other stuff. It's literally tell me where I'm called from. These are all of your xrefs. This is fantastic. Literally dot callers. You could do dot callees too. So if you want to know what functions are being called from a target function, just super nice. Like this just saves so much time. Gosh. All right. So source callers. If you haven't told, like if you can't tell yet, I'm a fan of Binary Ninja. So we have our source callers and source sinks. We do the same type of thing again, where we're looking at the intersection of those two sets to see if there are any interesting functions left. Meaning, we looked at all the locations where our sources were called. We looked at all the locations where our sinks were called. And if there's any overlap between those two, like a Venn diagram, then that's where we want to aim and focus. And it turns out there was overlap. There are these three functions that overlap. So both of the, or all three of these functions call a source and a sink, at least one source and one sink. Okay. So now when we start digging in, this is where things get interesting. For this, I could say function, which is just my normal function object. So for example, here I could do current function. This is all defined by Binary Ninja, just like I can do BV to get a binary view. So if I have my current function, then I can lift, this is like the disassembly view. I can lift that up to or reference high level IL or medium level IL by just doing this. I can get the SSA form by just doing SSA form. We won't be messing with SSA form, but it is really nice if you're doing more complex pattern analysis or like bug analysis and stuff. It helps out so much. So in this particular case, we have HLIL. And when we iterate over that, so for every basic block, and then we're going to go for every instruction in every basic block, okay? So those instructions have operations. This is not a surprise. So if I clear this and I go to current function.hlil, the other thing I could do is also just current HLIL, which is shorter. 288, that's this function. This function has, or this operation has a call type, right? If I do the same thing at 299 and do operation, it's an assignment, so an HLIL assign, okay? So it sort of makes sense. So I'm going to be looking for all the calls. Problem here is that sometimes, and there's one location where, and let me see if I can actually find it. There is a location, I think in here, where it does one of our assignments, level IL, but it's like this. So you end up having a function being called, but there's an assignment here. So it's not a function call as the outer layer, like the true operation. If we went to this location and index to 17, this is the, was not expecting HLIL var init, but it's initialization for this variable, which is sweet. I didn't even realize that was a thing. So this is a location where that variable is being initialized. So the really cool thing here is that at this particular point, we have to make some assumptions that either we're going to just be looking for calls, like at this location, this would be a call. At this location, this is either an HLIL var init, and these are the two. So I wonder what this is like multi or something, or what this ends up being. Assign, unpack. Okay. So these are, I'm used to using medium level IL. So all of these types are kind of new to me. I don't really mess with this too much. I'm starting to a little bit more to try to take advantage of a lot of the optimizations that happen in Binary Ninja. But in this particular case, you have to consider all these different types and unpacking these. So sometimes it's best to just say, all right, what I'm going to do is peek into the function, and doing that like prefix operands is probably the best way, because here then we can scan this to see if there's any type of call, and of course there is a call here. Then we can try to dig into it more. So that's probably the best way to think about this type of problem. Instead, I did a HLIL assign. So if it is an assignment, we're also going to take the source of that, which is going to be sort of like what is being assigned to it. And if that operation is the output of an HLIL call, then we'll look at that too. I'm basically going to create my own instance of the instruction, and it'll either be the instruction if it's a call, or the instruction source, meaning where it's coming from, the output of that call. So there's a potential here, and this is what I talked about, like Binary Ninja being a little bit more pedantic, is there's just lots of different types, lots of different operations. And if you took this out and just assumed, well, I'm looking for calls, right? You're going to miss things. So there's a lot of kind of printing stuff out and making sure you're dealing with the right things, looking at concrete examples, trying to understand this. This is where just kind of getting a sense of the overall API is really important. So going to api.binaryninja or api.binary.ninja is excellent documentation with examples too. So a lot of this stuff is really well documented, but it takes time to learn this, right? So at this particular point, we have this form, this HLIL call instruction, which we've isolated, and we've used a couple different ways. If I looked at this, for example, if this was a call to system, I would not be finding that, because I'm not utilizing the right types when pulling out that. So I'm not looking for an HLIL var init. So I would just miss it, right? So these are an upside, but a downside. You just have to do more work to make sure you pull all that stuff out. Maybe somebody has a better way to handle this particular case when I'm trying to isolate call targets, right? Maybe what I could do is do callees and see, like, maybe this would show up as a callee, and I can go to that location and pull that out rather than going down every single instruction saying, are you a call, are you a call, are you a call? It might be better to just do that. So different strategy. Either way, at this point we have enough to do analysis. So I'm going to go ahead and get the destination location. So this is basically going to tell me where is this target going, right? In our analysis, it's not going to show up as like snprintf or system. It'll be an address. So I get that address, get the function there, and then this is our call target. The way that I'm able to show snprintf in system is because I just use the call target that we got and say it with a name. The nice thing about getting parameters is I don't have to do this sort of like, I guess it wasn't really that hard in Ghidra. It's just different. Just being able to index into it. So you say, all right, here's my instruction. Give me the parameters. And for a call type, the 0th index is going to be your first parameter, which is what we're interested in, right? So once we have that, if it is an address of, then I'm just stripping off that reference. So what we'll see is you'll see like an ampersand, like this will be an address of. So I just want that variable now just to consider those two things together because we're doing like just a naive string match. So at that point, we put those into params. I do param1.var. That'll give me the variable for this guy instead of like there's for SSA form, there's like a version and other things, right? So that var will give me what I'm looking for. So I'll put those into source args and sync args. After that, we will again do the same thing, looking for the intersection of these two. And if they match, it means that the source and the sync that we looked at have the exact same thing, right? The exact same variable, which is what we're looking for. And that's what happened here, right? So if we go to this particular location, which is the location of this alert, what we'll end up seeing is we have system here, and there's sprintf into this string. So this is a Lua command that's being kicked off. This %s is what we can essentially inject into, knowing from the Flashback team's analysis, and that this is something that we can actually taint with user-controlled data. That being passed into this, and then being executed here is what causes the issue, right? So still pretty much the same type of analysis. We use the 3 kind of shot method where we're sort of like putting pebbles into like screens and shifting them out. So we throw the whole binary in and say, are you even interesting for me to look at for this type of audit that I'm trying to do? And if anything falls through the mesh on that one, then we go to a finer one and then a finer one. And then finally, we're starting to look at parameters and stuff. There's no reason to start looking through every single operation in this, looking for system calls and then grabbing its parameter. We want to fail fast, fail early, so you can move on to the next thing. Because in practice, we're throwing this against hundreds or thousands of binaries, and we're hoping to get details really quick. The hope is that we can take this type of analysis and tell a human like, hey, these are the areas we probably want to spend a little bit of your time. And in practice, using this type of method, what we found is that we can get a list of even hundreds of these. And, a decent vulnerability researcher or reverse engineer can go down that list really, really quick and knock those out and say, yes, this is interesting. No, this is not interesting. And here's why. And that gives a lot of credence, I think, to, I said that word, I don't even think I know what it means. that gives like a lot of opportunity to put your effort elsewhere for the really interesting things and letting sort of these automatic analyzers go and start finding issues. When people are fuzzing, typically what they'll do is throw a dumb fuzzer at something while they're building up their models and trying to build like better understanding of how fuzzers work before things were, really nice genetic algorithms for mutations and things like back in the day when you're using a peach fuzzer or something. You throw really dumb models at it and just let that go while you start putting your time and effort into reverse engineering and then refining what that model looks like so you're generating more real world inputs. This is sort of the same thing. We want to throw, our static analyzers or cheap analyzers at stuff while we take, the cognitive complexity off, that burden off of our human researchers so that they can focus a little bit more on just the stuff that falls through the screens, right? So hopefully that's interesting to you. This type of thing can be done in pretty much any binary analysis framework. We could definitely do this in IDA. We could definitely do this in Anger or Triton or something like that. So if there's something else that you want to see, let me know. Otherwise, thanks for watching.